Okay, so we have looked at how vibrations in mechanical systems can be modeled as a differential equation which we can solve using our machinery. And so we looked at these three different possibilities for a damped harmonic oscillator, how you can have underdamped motion which leads to oscillatory motion, or critically damped or overdamped cases which give you non-oscillatory uh, decaying solutions, right? All of this we worked out using using our machinery from differential equations. So here you will look at the next interesting scenario which comes in if you also have an external force that you're applying to the system, right? So in the theory of differential equations, we thought of these as inhomogeneous differential equations. Here it's the physical picture is to think of them as an external drive being applied to your system. So these are what are called driven harmonic oscillators, if you wish. That's the topic for this lecture. Okay, so we have a mass m, and it's attached to a spring with spring constant k, and there's the frictional force. We look at a damping constant of L associated with this frictional force, which is proportional to the speed of the mass, and there is an external force, right? So the external force can be more general than what we consider here, which is f times cosine of omega naught t. But this is completely this is a very standard type of external force. So if we understand this, then it opens up our understanding to many other kinds of drives. So we look at periodic drive with frequency omega naught and amplitude f. And so the differential equation here is just m times d squared x by dt squared plus L times dx by dt plus kx is equal to f times cosine of omega naught t, right? So it's useful to define these quantities. Omega naught squared is equal to k by m, to b equal to L by m, like we did earlier, and also introduce a small f is equal to f by m. So our differential equation now becomes d squared x by dt squared plus 2b times dx by dt plus omega squared x is equal to f cosine of omega naught t, right? So you see that there's omega, there's also an omega naught, right? There's a knob with as far as omega naught is concerned, which is in our hands, which we can control. And so we will see how the interplay of these different frequencies leads to interesting phenomena. So we already solved for the homogeneous equation, right? So we just need to work out a particular solution here. So let's say that we focus on the underdamped case, right, for concreteness, right? I mean, you can also work out the full general solution for the critically damped case or the overdamped cases, but you will see that basically it's the particular solution which is of particular importance or of interest here, right? So we will argue how for long times the particular solution there is what will dominate the dynamics of such a system. Okay, so the complementary function here is just a sine of beta t plus cosine of beta t, the whole thing multiplied by e to the minus bt, as we have already seen. And so where of course beta is defined as square root of b omega squared minus b squared, right? So this is the case where omega is greater than b, so omega squared minus b squared, taking the square root of this quantity is not an issue. Okay, so to find a particular solution, we look for a particular solution of this form: c times sine of omega naught t plus d times cosine of omega naught t. This is a trial on sorts that we make, right? So we have seen how the particular solution should be made to mimic the drive, the external externally applied force, right? So both cosine and sine, they have to go together in pairs. So we have to consider both of these: c sine of omega naught t plus d cosine of omega naught t. And then if we differentiate this, then you have c omega naught cosine of omega naught t minus d omega naught sine of omega naught t, a second round of differentiation, and we get a minus c omega naught squared sine of omega naught t minus d omega naught squared cosine of omega naught t. Now we have to just plug these expressions back into the original differential equation. So then we have d squared x by dt squared plus 2b dx by dt plus omega squared x. So we plug in for each of these quantities. We have here the second derivative, the first derivative, and the ansatz itself, which is here. So if we plug in these expressions, and then we must equate it to f cosine of omega naught t. So basically we have to ensure that the coefficients are such that, this is a method of undetermined coefficients. We have to ensure our coefficients are such that, omega naught 2bc plus omega squared minus omega naught squared times d, this is the coefficient corresponding to cosine of omega naught t. So on the right hand side we see that this coefficient must equal f, and there is no coefficient corresponding to sine of omega naught t. So then we see that this will immediately imply that omega squared minus omega naught squared times c minus 2b omega naught d must be equal to 0, right? So now it's a it's a coupled linear equations, two linear equations and two unknowns. So we know how to solve this, and so if you solve it, you'll get c is equal to 2b omega naught f divided by omega squared minus omega naught squared the whole squared plus 4b squared omega naught squared, and d is just omega squared minus omega naught squared the whole times f divided by omega squared minus omega naught squared the whole squared plus 4b squared omega naught squared. Right, once we have solved for c and d, we just plug these constants back into the particular solution, and our particular solution is just f over omega squared minus omega naught squared the whole square plus 4b squared omega naught squared, this entire thing multiplied by omega squared minus omega naught squared times cosine of omega naught t plus 2b omega naught times sine of omega naught t. You should check this, right? So it's fairly straightforward algebra is involved, but you should be careful and make sure that it's all correct. So now it's useful to rewrite this particular solution that we have obtained in a form which is instructive, right? So we can think of this as well, I mean, there should be a square root here. So there should be a square root here, so which we can put this back in. So so there's a square root here. So f divided by this quantity okay, so there is so f divided by square root of this quantity times cosine of omega naught t minus phi, where tan phi, so you observe that you have something like cosine of omega naught t cos phi plus sine omega naught t sin phi, right? So that's cosine of omega naught t minus phi, and then you have to arrange these terms in such a way that that you figure out what phi is. So here you can check that indeed phi must be chosen such that tan phi is equal to 2b omega naught divided by omega squared minus omega naught squared. So what this tells us is that, so if you're driving your system at a frequency omega naught, so the particular solution is also going to have the same frequency, but it has a frequency, there's a phase difference, right? So the solution is out of phase by an amount phi, which is given by this quantity. So the full general solution, finally we can write it as x of t is equal to the complementary function plus this particular solution, right? So once again, so we are missing this square root. So we'll plug this in and put it in here. Okay, so we observe that in the limit t tending to infinity, so you see that this first part, the complementary function, becomes less and less relevant as more and more time elapses, right? So it doesn't matter in which regime you're driving the system, whether it's underdamped, overdamped, or critically damped. So there is going to be always this kind of an exponentially decaying term. So for large times, basically this this complementary function is going to become irrelevant for as time tends to infinity. So that's the reason why. So this particular solution in this context is also known as the steady state solution, right? So your system for long times will settle down to the steady state, and whatever information is contained in the complementary function is actually what are called transients, right? So it's important only if you're interested in how the system behaves at very, very small tiny times right after this external driving force is introduced, and then basically the external drive takes over, and then so the system is entirely under the control of the external drive for long times, and we see that the motion is going to be periodic with exactly the same frequency as the frequency of the external drive, and there is a certain phase difference which appears in between the motion of your particle and the externally applied drive, right? So that's what this solution tells us. That's all for this lecture. Thank you.